Okay, we're going to see how the spanning tree protocol functions in a network with redundant switches like this. First of all, we can get some sense by just looking at the link lights and seeing how certain ports have been put into a blocking position. Now, all switch ports on a switch, when they come up, they go from blocking to listening to learning to forwarding. And when they get to forwarding, we should see these green lights, right? So, and then there's also, of course, shutdown state, which means it's been administratively shut down. Now, I shut down all the ports on these switches, and then I activated the ones that we're using just on the links that you see. And you can see that some of these are green, which means they're forwarding, and then some of them are orange, which in this case means they're blocking, except they're blocking not because they were shut down, right? But they're blocking because STP, Spanning Tree Protocol, put them into a blocking state because it designated them as what we would call non-designated ports. So they're in a blocking state. Now you see over here, I've got the port designations that Spanning Tree uses, right? So you've got root ports, designated ports, and non-designated ports. Now, if we look at this switch right here, we can see right off the bat that the root port is probably this green light right here, which is a gigabit port, and it's going this way. And the root port is the port that is closest to the root bridge. Well, these two ports are going forward, let's say, and let's say these two ports are going backwards, right? So we've got, this is the root port. These two green ones right here would be, let's say, designated ports, and then this orange port right here would be what's called which would be called a non-designated port or a blocking port, and it's blocking a loop on the network, right? And so this is the type of thing that Spanning Tree Protocol does automatically. Now, when Spanning Tree Protocol first, let's say, starts up on the network, you have a network like this, the first thing that has to do is figure out who's going to be the root bridge. So the first thing it needs to do is figure out who's going to be the root bridge, or you could call it the boss switch, right? And the root bridge is the switch from which all spanning tree algorithm calculations are done according to. So, we have to figure out, let's say, Spanning Tree Protocol figures out who is the root bridge of all the switches in the network. So right now we're looking at this network of all these switches. It's all VLAN 1, right? And Spanning Tree Protocol is working. We can see that certain ports have been shut down. So one thing we want to do, find out first of all, is who is the root bridge. Now, if you go over here, we'll say the root bridge is based on the BID or bridge ID. It's used to determine the root bridge. And usually it's who has the lowest bridge priority number, and by default, all of the switches have a bridge priority number of 32,768. And then you add on the VLAN ID, which in this case everything's VLAN 1, so all of these switches have a bridge priority number of 32769, or 32768 plus 1 equals 3276869. Now, if they all have the same bridge ID number, how do you pick the root bridge? Well, they all have the same number, so there's no lowest number, so you have to go to another factor. Another thing that the bridges have is an extended system ID, and it's the ID for the VLAN, right? Now, in this case, they're all on VLAN 1, so that's not going to be an issue. So the root bridge, the last determining factor that determines the root bridge is the lowest MAC address, or the lowest MAC address, the active MAC address on the switch, and you get the lowest one, that will be the root bridge. So, and when Spanning Tree Protocol first starts up, what happens is the protocol sends out BPDUs, right, or Bridge Protocol Data Units, and those are messages, or Spanning Tree Protocol messages that are sent switch to switch, and every switch identifies who the root bridge is and what their bridge ID is. And to begin with, every switch assumes that it is the root bridge. But as the messages go back and forth on the switches figure out who has the lowest BID or bridge ID, and then that switch by consensus becomes the root bridge. So let's take a quick look. We'll start by going to this switch right here. We'll open it up, and I've just opened it. I'm going to go straight to the command line interface, and I'll type enable and conf t to get to global config mode. And now I'm in global config mode, and I want to run one of these commands. So the command I'm going to run is the show spanning tree command. So we'll say show, and actually I'm not going to do that from global config mode. I'll do that from privileged mode. There we go. Show spanning dash tree. And when I do that, I'm given some information, and you can see this information says that it's VLAN 1, spanning tree protocol is enabled, the root ID, right, for the root bridge, right? So the root ID of the root bridge is priority 32769, just like I said, 32768 plus 1 is 32769. And then here's the MAC address of the root bridge, or the boss switch, essentially. Then over here, you'll see this is the bridge ID. Now this is this switch's ID. Now if its MAC address matches the MAC address of the root bridge, then we know that this switch would be the root bridge. But in fact, you see that its MAC address is different than the MAC address of the root bridge. So this switch is not the root bridge. But if we expand this, lowers down, you can also take a look at its ports. So let's take a look at its ports, and we're talking about this switch down here in the corner. It's got a blocking port here, forwarding, and then forwarding. It has 3 active ports, and you can see that one of its ports is in the role designated port forwarding, right? Another port is, it says alternate or non-designated, and it's in the blocking state, right? Notice the cost. And then the root port, which is the port closest to the root bridge. So, and this one is Fast Ethernet 24, right? Well, if we look at this switch, you can see that Fast Ethernet 24, sure enough, is this green link right here, and it's the closest one to the root bridge, so it's going this way. Now, does that mean that this switch is the root bridge? No, it just means that this is the closest way to get to the root bridge, right? Now this is the designated port. Notice it's going here. And then this is the blocking port, non-designated port, going here. All right, let's keep looking around the network. I'll close this, and you go to the next switch and run the same command. And we'll type enable show spanning tree. And you can see that this switch, right, and I'm talking about this switch right here, right? This switch is also not the root bridge. Notice the MAC address of this bridge, or this switch, is not the same as the root bridge or the root ID, right? It's just not the same. And then you can see the ports and which ones are in, which one is the root port. Designated ports, which are in forwarding mode, and then non-designated ports are alternate ports that are in blocking mode. And we can see that this switch right here has a root port going this way, a blocking port going this way, shutting off a redundant path or a loop, and then 2 designated ports going back this way. Now, it's interesting that this root port, let's do a little more analysis about this switch. This switch has Fast Ethernet, Fast Ethernet, Fast Ethernet, but it has a gigabit port right here going this way. So this is the fastest port on the switch. The other ones are 100 megabit, and this one is gigabit going this way, right? Well, no wonder it's the gigabit port that became the root port, right? Notice the cost is a 4, whereas the Fast Ethernet ports are all cost 19. Well, basically, when Spanning Tree Protocol figures out which ports to shut down, it figures out what are the fastest paths to the root bridge on the network. And it's going to do that by a factor of cost. And I've put down here the cost values. A 10 gigabit port gets a cost value of 2. A 1 gigabit port gets a cost value of 4. 100 megabit gets a cost value of 19. And a 10 megabit Ethernet port gets a cost value of 100, right? So what you have here is this is a 19, right? From here to here is a 19. And then this one is a 4, right? So you've got a cost of a 4 between these two links, right? As opposed to this one, which is a 19, right? So this link is a 19, this link is a 4, so it's no wonder that the switch chose this port to be its root port, the closest one to the root bridge, and it put this one in a blocking state as a non-designated port, right? So we can keep going around the network to do some more examinations. So we'll go to this switch now, which has this gigabit link, and maybe this switch is the root bridge, right? All indications are pointing that it could be this one right here. And so we'll go here and we'll take a look. Tab and then enter. Did the show spanning tree command. We'll take a look here. Okay, show spanning tree. Now once again, I'm using this layer 3 switch that's up here at this core layer right here. Let's see if it's the root bridge. And we can see here that the root bridge has a 5D32 address at the end here of the MAC address. And this bridge, this switch, has a 116A MAC address. So this bridge is also not the root bridge. Well, that's curious. Okay, so let's take a look at its ports. So we'll go down to its ports and we see that it's got all of its ports are in a forwarding mode, which is pretty curious. Typically, if all of the ports are in a forwarding mode, that would be the root bridge. Its root port, right, which is the port that is pointing the closest to the root bridge, is gigabit 01. Notice the cost value 4, right? So this root port, gigabit 01, is pointing towards the root bridge. So let's take a look at which one that is, right? Well, you can see that this switch right here, the gigabit 01, is the port that's going this way over to this switch. So indicating that probably this switch right here is probably the root bridge, right? Now I'm going to leave this open. I'm going to go to this switch. And we'll open this one up. Command line interface, enter, enable, show, span. And you can see that this bridge is indeed show spanning tree, the root bridge's MAC address, this bridge's MAC address, that this switch is the root bridge, or the boss switch, so to speak, in the spanning tree algorithm, right? All of its ports are in a forwarding state. Notice it doesn't have any root ports. Root ports are for switches that are pointing towards the root bridge. The root bridge has all of its ports in designated or forwarding mode, but it doesn't have any root ports because root ports point to the root bridge. Notice the priority number on these ports. The port value, the default priority number of these ports is 128, and then the number of the port. So this is port 22 on the switch, port 23, port 24 on the switch, port 25, and port 26. And they have a default priority number of 128, and I'll talk about that in a minute. So anyway, so this switch is the root bridge in the network.